As we review over the ideal gas equation, we will have a combination of Boyle's law, Charles' law, and Avogadro's law coming in to form the ideal gas equation. Now right here is the ideal gas equation, PV equals nRT. Now this gives students more difficulty than any of the other gas equations, and the key thing that you must be aware of is that in order for this formula to work, each of these components, pressure, volume, number of moles, constant, and temperature, must be in very specific units. So when performing the ideal gas law equation, PV equals nRT, each of the components must be in specific units. Pressure must be in atmosphere, volume must be in liters, N is the number of moles, R is an ideal gas constant of 0.082. The units are liters times atmosphere over moles times Kelvin, and temperature must be Kelvin. Now, if you do not use these units, you will get the wrong answer, and that is the most common mistake students make when doing ideal gas law problems. These are simple algebraic problems you fill in and solve for x, but if the units are wrong, the answer will be wrong. Let's look at an example. Now the best thing to do when approaching these problems is to write out your equation and find out which components you have, what you must solve for, and then are your components in the correct units. Here we have the example. What is the volume in liters occupied by 49.8 grams of hydrochloric acid at STP? Now when we first look at this problem, it looks like we don't have a lot of information to work with. However, STP does give us temperature and pressure. Temperature at STP is 0 degrees Celsius. That needs to be converted to Kelvin. We have the formula Kelvin equals Celsius plus 273.15. So we have our Kelvin. Pressure has to be in atmosphere. STP is 1 atmosphere pressure. We are given grams, however we need moles. So we take our 49.8 grams, 1 mole over the weight from the periodic table, and we now have our moles of HCl. Remember that N is a constant of 0.0821. We will solve for V. So we end up with volume equals nRT divided by P. Here we have our number of moles. R is our constant. We have our temperature. Here we have our pressure. Notice our moles cancel. Notice that our atmosphere cancels. And notice that our temperature cancels, leaving us a volume of 30.6 liters. One final example. Here we have tungsten that is used in light bulbs. We have our balanced chemical equation. Our question is how many liters of hydrogen at 35 degrees Celsius and 745 millimeters of mercury are needed to react completely with 875 grams of WO3. The equation we will be using is PV equals nRT. Now, the first thing we need to do is we need to convert from grams of WO3 to moles of H2. That will be a mass mole conversion. So we take our 875 grams of WO3 times 1 mole of WO3 over the weight of WO3 from the periodic table. We will use our coefficient ratios. Right here we have the 1, and right here we have the 3. We do our math. We get 11.3 moles of H2. Our pressure was stated as 745 millimeters of mercury. Now, because this is the ideal gas law, we need to have this in atmospheres. So we take our 745 millimeters of mercury. We use our coefficient, our equation of 760 millimeters of mercury equals 1 atmosphere. We do the math, and that's where we get the 0.98 atmospheres. Also, we had to do a conversion for our temperature. Our problem stated the temperature to be 35 degrees Celsius. Kelvin equals Celsius plus 273, and so we would have 35 plus 273 in order to get our temperature. Now as we look at the equation, PV equals nRT, we now have our pressure in the correct units, we have our temperature in the correct units, R is our standard, our number of moles is right here, and so we solve for V. It's a simple algebraic problem. When you do the math, you should get 292 liters.